So now we're going to talk about logarithms. So if we let a be a positive real number different than 1, then we say that the logarithm of x with base a is written as this. So y equals log base a of x. And the way this works is that this is true if and only if a is x is a to the y. And this is only true if x is positive and y can be anything. So note that there are two equations that are equivalent. The first one we say is the logarithmic form, and the second one is the exponential form. This is why we're doing this right after the exponential function, right? Now, if you have any problems with this, one way to know this is one student once told me about something called the snail method. So if we're going to convert that into its other form, so get the log on one side, y on the other, and what we're going to do is we're going to snail it up. So it's a, that's the first thing you hit, raised to the y equals x. And if you notice, it kind of looks like a snail. You can actually do that the opposite way as well, right? So if we want to rewrite it, we could say it's log base a of x equals y. And again, kind of looks like a snail. Cool. So let's change the following into exponential form. So we see that's going to be 5 squared equals u. So then u would just be 25. That's it. All right, part B. So if we want to put the w on the other side, make it a little easier on us maybe. So we can see it's 4 raised to the w equals 2t plus 3. And that's it. All right, now let's change it to the logarithmic form, so the other direction. So we're going to have log base b of 8 equals 3. Log base b of 8 equals 3. That's how you say that. All right, next one. We're going to have log base 3 of x equals 5 plus 2z. I'll make the 5 a little more 5-ish. There you go. All right. So let's do a quick word problem. The number of bacteria for a certain culture after T hours is given by this formula. So express T as a logarithmic function of n with base 2. So if it says express T as a function, right, then we need to make sure it's T equals. So we can put the n on the other side. So 1000, 2 to the t equals n. But notice, the way this has always worked is we had a raised to the y equals x, right? We didn't have a number times a power equals x. So we need to make sure to get rid of that multiplication. So we can just do that by dividing by 10,000. And now we can do it. So we get log base 2 of n over 1,000 equals t. And if we're going to write it as a function, so this would be if it was expressing this in terms of the other, but if we're going to write it as a function, we just need to make sure it's t of n equals log base 2 n over 1,000. So this would technically be the correct way since it said as a function of n. Functions have to have stuff plugged into it, like f of x. Good. All right. So let's find this number if possible. And let's try to do it without calculators. So if this equals some number, right, then we know that that will be 10 raised to some number is 100. So 10 raised to what power is 100? Well, hopefully you can just see it's 2. But if not, right, we can also break down the 100. So we know 100 is just 10 times 10. So that means 10 to the x is 10 squared. Same bases, so we can get rid of it. X equals 2. All right, let's do the next one. So if this equals some number, right, then we see 2 raised to what number is 32? Sorry, is 1 over 32. Well, first things first, right? We got to get that 32 out of the denominator. So we can just make that 32 raised to what power? Hopefully you said -1. Good. And then how can you break up 32? So 32 is 4 and 8, which is 2 and 2, which is 2 and 4, which is 2 and 2. So it's how many 2's? 5. So 2 to the x is the same as 2 to the 5th to the 1st. So if you have a power raised to a power, you just multiply those powers. So then that means x is -5. All right, let's do this one. So so that means 9 raised to what power is 3? So 9, of course, is 3 squared. So we can rewrite that as 3 squared to the x equals 3. So multiplying the powers, 3 to the 2x equals 3. So what power is 3 being raised to? Remember, it's the first power. So that means 2x equals 1. So x is 1/2. All right, next. Log base 7 of 1 is what? So that's going to be 7 raised to the x equals 1. Well, that might be a little hard to think about, but let's just think about this. What number, if you raise 7 to it, or really any number to it, is going to equal 1? So hopefully you remember that's 0, right? Anything to the 0th power is 1. Which, side note, can we just go back and look at all these? Like, isn't that crazy? Like, before you knew this, did you know that you'd be able to do log base 9 of 3? No, that's crazy. But now it's 1/2, and you didn't even need a calculator for that. Isn't this crazy? All right, last one. So you can say log 3 raised to the x power is -2. So 3 raised to what power is -2? Well, these don't really have the same bases, so that's not going to help. Let's look at 3 to the x, right? If we graph that, when does it land on -2? It doesn't, right? It can only go as far as 0, but can't actually touch 0. So this doesn't have an answer. That doesn't make any sense. Which, if you remember, we said any number inside a logarithm has to be greater than 0 for you to actually do it. So let's talk about the graph of a logarithmic function now. So if you have any log, right, where a is positive, that base is positive, you're going to have 3 points. So the first point is going to be 1, 0. The second point is going to be a1. The third point is going to be 1 over a, -1. These actually may look similar, right? So if you go back to our exponential function, right, these are just flipped. Right? These points that we graph for the exponential functions, they're just flipped with the x and y, which makes sense, right? If y is log base a of x, right? Oh, if we want to do it in our way. So that means it's a raised to the y equals x. And isn't that the inverse of a to the x equals y? Yeah, right? So these are actually inverses of each other, the exponential and the logarithm. All right, so if we graph it, we see that we're going to get 1, 0, A1, and then 1 over A, negative 1. So it's going to look like this. This is what a regular logarithmic function, if A is positive, looks like. So this time we have an asymptote at x equals 0, which again makes sense. We flip the x and the y. So the asymptote is going to be at x equals 0 this time. So looking at this, right, what's our domain? What can we have for the x values? We see that it's going to be 0, infinity. And then what about the range? We can go all the way down and all the way up. So the range is negative infinity to positive infinity, which again makes sense, right? Because these are flipped when it comes to the exponential, which is what we always said, right? The inverse, the range of an inverse is the domain of the function, right? So the range of a logarithm is going to be the domain of the exponential, and vice versa, right? The domain of a logarithm is the range of the exponential. We just flip those. All right, let's do some quick sketches. So we got log base 3 of x. So if you do a quick sketch, right, 3 is bigger than 1, so that's what we're going to get, right? Just a regular old graph. What about negative? What happens when you have a negative inside with an x? So hopefully you remember your transformations, and we're going to flip it across the y-axis. Right, it's a reflection across the y-axis, so that's what it'll look like. All right, we subtract 2 inside, we can make that equal to 0. So x is 2, which means we're going to the right 2 units. So instead of it landing at 1, it's going to land at 3. And the asymptote will be here. All right. If we have it on the outside, it's going to go down 2. So instead of landing at 0, it's going to land here. All right, let's do 2 minus x. So if we got 2 minus x equals 0, we see that x is actually positive 2, right? Which means it's going to go to the right 2. But what's the first thing that actually happens to this function? Hopefully you see the first thing that happens is that negative, right? So we know that log base 3 of x is going to look normal, right? Log base 3 of negative x is going to go across the y-axis. And then our official function, when you add that 2, is going to shift over 2. So this is what our function looks like. All right, last. What if you have an absolute value inside the x? So x is still going to be the same values, but whenever we have a y value, right, that's all going to be positive now. So it's still going to be at 1, 0 goes up, right? But anything between 0 and 1/2, instead of going down, is just going to go up. And that's it. All right, so find the logarithmic function of this form that contains this point. So we see that it's 3 equals log base a of 8. There we go. So if we want to rearrange it to be in our snail form, we can see a raised to the 3rd power equals 8. So basically we need to figure out what is that base? Well, we can break up 8 into 4 and 2, 2 and 2, right? So we can see that that's 2 to the third, which makes it pretty clear that a is just 2. So the function, if you write it all out, is going to be f of x equals log base 2 of x. All right, we're just flying through these. Okay, so logarithmic base, we can see, right? So if you look at it, if we graph our log function, right, we can see that it also is 1 to 1. Right? So we also have a 1 to 1 function. And because of that, right, we know that if we plug in f of a and f of b, we're going to come out with a equals b. But since we already have an a in our actual equation, right, that might be a little confusing. So instead, let's just plug in f of x1 and f of x2. So if these are equal by 1 to 1, right, the definition of 1 to 1, we know that x1 equals x2. And so what did we say f of x1 was? Right, for a logarithmic, it's going to be log base a of x1 equals log base a of x2. So if we have log with a base equals log of the same base, right, we can just get rid of the logs. So kind of like the exponential rules that we did earlier. So now we're going to try to get, instead of a base to a power equals base to the same power, we're going to try to get it to have a log with a power equals log with the same power. Or sorry, log with a base, log with the same base. So let's solve some equations. So we got log base 6 of something, log base 6 of something. So we can just get rid of those logs. So we get 4x minus 5 equals 2x plus 1. So that means 2x is 6, which means x is 3. Now, the only problem with the logs is that you have to check, because what did we say the domain of a log was? It was from 0 to infinity. And that doesn't mean x is 0 to infinity, it means whatever you're taking the log of has to be between 0 and infinity, right? So because of this, you always have to check for logs, right? So if we have, so let's just do a quick reminder list of, and then we'll go back and we'll actually check. So let's do a quick reminder list of all the restrictions to our domain. Right, we've talked about a couple. So hopefully you remember the first one we talked about were fractions. Right, when we have a 1 over x scenario, we're gonna have a restriction to the domain, so we gotta check ourselves if we're doing these kinds of problems. The second one is gonna be even radicals. Right, square root of x, fourth root of x, those kinds of things. So if you start with this in your formula, you need to kind of check yourself. The other things that we've talked about so far are the trig stuff, right? So tangent of x, secant of x, cosecant of x, cotangent of x. These are all things we had to check too, remember? And then now we need to check logarithms. So here's our list so far of things you have to check when you're doing problems. So since it started with a log, we gotta check ourselves. So we can just plug it into the initial logarithm, right? So that's actually how we can check. So 4 times 3 minus 5, right? That's 12 minus 5, which is 7. That's positive, we're all good. And then you got 2 times 3 plus 1. 2 times 3 is 6, plus 1 is 7. Greater than 0, all good. Okay, so our actual answer really is x equals 3. Let's do the next one. Okay, well, we don't have log equals a log, so what else can we do? Well, hopefully you see that we can turn it into our other form. So that's something else we can also do. If we don't have a log equals a log, we can always just turn it into the other form. So 4 raised to the third equals 5 plus x. So 4 to the third is just 64, which means x is 59. Do we have to check? Yes, because we started with a log. So 5 plus 59 is just 64. That's bigger than 0, so that is an answer. We're all good. All right, let's talk about some special logarithms. We'll do some more problems like this in the next sections as well. So some special logarithms. So if a logarithm is called a common log, it's because it has a base of 10. And basically the way we write it is we just write it log x. So if you see log of x without anything, that's just going to be log base 10 of x. And of course, x has to be positive. The natural log is when it has a base e. So natural log looks like this, ln. Someone clearly who wrote it is dyslexic. So when you see natural log, that's just going to be log base e of x. And basically these occur so often that they just get their own symbols for it. And again, that's when x is greater than 0. All right, so let's look at this. So let's turn log x equals 2 into the other form. So we know, since nothing's written there, it's log base 10, right? So it's going to be 10 raised to the second power equals x, or x is 100. Okay. We said natural log has an e, right? So that's raised to the e, or that's the base of an e. So we got e raised to the y plus 3 equals z. And that's our answer. All right, so now let's turn this one into the logarithmic form. So we're going to have log base e of x equals 2. But this is the incorrect form, so instead of log base e, we just write natural log of x. And you do need to do that. So we do need to make sure we're writing natural log of x, not log base e, ultimately. Good. And then for this one, it's going to be log base 10 of z equals y plus 3. But again, log base 10, that's just log. All right, let's look at 2 word problems and then we are done with this section. So the magnitude r is going to be in this form. So if the intensity of the earthquake is 1,000 I naught, let's find r. So I is the intensity. So if the intensity is just 1,000 I naught, that means r is going to be log of 1,000 I naught over I naught. So r is log of 1,000, right? And what do we say if it's just log? What's the base? That's 10, right? So we know log base 10 of 1,000 equals r. So if we want to put it in the other form to make it make a little more sense to solve the problem, we see 10 raised to the r equals 1,000. Hopefully you can see, since there are 3 zeros, that's the same as 10 to the third, right? So r is just 3. Do we have to check ourselves? Well, in this case, we weren't plugging R wasn't inside the log, it was outside the log. So there's nothing to check this time. All right. So now let's express I in terms of R and I naught. So we have R equals log of I over I naught. So if we rewrite it to our nice form, we know we're going to get 10 raised to the R equals I over I naught, because we're trying to get I all by itself, right? Express I in terms of R and I naught. That means I needs to equal something with R and something with I naught. So to get I by itself, we just multiply, right? So I is going to be I naught times 10 to the R. We can write it like that. All right, last problem. Newton's law of cooling states that the rate at which our object cools is directly proportional to the difference in the temperature between the object and its surrounding. So we can see that for T being temperature, big T being temperature, little t being time, this is the formula for it. So according to this equation, what is the initial temperature of the object? So the initial temperature is going to be little t is going to be time for what? How many hours has passed at the initial? Hopefully you see it's 0, right? So we can just plug that in, 75e to the negative 2 times 0, which is just 75e to the 0, which is 75 times 1. So the temperature is 75 degrees Celsius. The other way you could have done that without having to do any of that math is just noticing, oh, this is our same formula of A equals PE to the RT, right? And P is the initial. So 75 is going to be your initial. So approximately how long, let's do it in minutes and hours, would it take for the temperature to half itself? So if we know that the initial temperature was 75 degrees, then half of 75, that temperature is going to be 37.5. So we just need to solve for t. So we're going to have to do, we're going to change it into our logarithmic form, but remember, we're multiplying first, so we have to get rid of that multiplication. Doesn't work if you do that, right? So we divide both sides by 75, and we see if we want to put in our form, e to the negative 2t is just 1/2. Okay. So to put in our other form, we see it's log base e, which is natural log, of 1/2, or 0.5, equals negative 2t. So we can see that t is going to be negative 1/2 natural log of 0.5, which is about 0.346 hours. So if we multiply that by 60, we see that we get about 21 minutes. So it's going to take about 21 minutes to half the temperature. All right, and that is it. So if you have any questions, like always, feel free to email me. Other than that, have a great day.